Alright, by this point in time I think most of us are kind of tired of finding the derivative using the limit of a difference quotient, and so starting with this lesson we're going to start developing shortcut rules for finding derivatives. Make sure before you look at rule 1 there's a little section in text in the lesson about higher order derivatives and their notation above this. Make sure you give a quick read through that and understand the notation for higher order derivatives, because we're going to apply that as we move forward. But here we go. Our first rule for shortcut for derivative: if we have c as a constant, then the derivative with respect to x of c is 0. And you see the proof written out here. If we suppose f of x equals c, then we set up the limit of the difference quotient. And since f of x is equal to c, since it's constant for all values of x, that means both of these things are c. We substitute those into the limit of the difference quotient, and now we end up here with a limit as h goes to 0 of 0 over h. So what we have is we have something that is 0 over something that's approaching 0. And if we pick any value for h other than 0 as it's approaching 0, we're going to have 0 divided by some finite number, and so that's going to be 0, and therefore our derivative is 0. That's the proof that this rule works. Let's take a look at the example of this. Not too hard. If y equals 6, we're going to find dy dx. Well, 6 is a constant, and therefore dy dx is equal to 0. Okay? Alright, let's move on to rule number 2. The power rule for positive integer powers of x. If n is a positive integer, then the derivative with respect to x of x to the n is equal to n times x to the n minus 1. And we're going to prove that here. We're going to suppose n is a positive integer. Then the derivative with respect to x of x to the n using the limit of the difference quotient is the limit as h goes to 0 of the quantity x plus h to the n minus x to the n all over h. And now I'm going to expand this x plus h to the n, which is a little bit difficult to necessarily think about because we have an unknown integer exponent. But think about what happens when we expand x plus h to the second, x plus h to the third, x plus h to the fourth, etc. There's a very distinct pattern that we can come up with, that we can see whenever we expand something of the form x plus h to the n. And we're going to utilize that to our advantage here. This is going to be the limit as h approaches 0 of x to the n plus n to the times x to the n minus 1 times h plus some other constant times x to the n minus 1 n minus 2 times h squared. We have all these terms kind of in here, all the way down to h to the n power, whatever that power is. And that's the expansion of x plus h to the n. Now notice that we have an x to the n and a minus x to the n. Those are going to cancel each other out and get us to our next step, which is that this is the limit as h goes to 0 of n times x to the n minus 1 times h plus all these other terms plus h to the n excuse me, all over h. Now, every single one of these terms has an h in it, and therefore I can factor in h out of all of those terms, and this turns into the limit as h approaches 0 of n x to the n minus 1. So I forgot to factor my h out. Let me start that phrase over again. So this is going to be h times x to the n minus 1. I'm struggling here. Let's give it a third shot. I think I got up too early this morning. N times x to the n minus 1 plus a bunch of other terms all the way down to h to the n minus 1 all over h. Now, all of the remaining terms that are inside my ellipsis here, as well as this last term, they all contain h's. So when I cancel these h's out, I now have the limit as h approaches 0 of quantity n times x to the n minus 1 plus a whole bunch of other stuff plus h to the n minus 1. And all of these terms contain h. And therefore, when I substitute h in to take my limit, all of those terms become 0. And the limit of this is just going to be n times x to the n minus 1. And that is exactly what we want the derivative with respect to x of x to the n to be equal to. And so we're done. Throw in an old school QED there. And there's our derivative rule, our power rule, for any time we have positive integer powers of x. So anytime we have x raised to any positive integer power, we can apply this rule. And we're going to go ahead and do that in this example. First, find dy dx for y equals x cubed. So dy dx is going to be, and all the rule says is bring the exponent down in front and lower the exponent by 1. And that's the derivative of x cubed. Do the same thing here in part B. I've got dy dx equals 6 x to the 5th. Alright, that's where we're going to stop for this video. Join me next time where we're going to look at rules 3 and 4 of our shortcut rules for derivatives. Have a great day.